Okay, hello everybody. Thank you very much. It is my immense pleasure to welcome you to our second keynote of the IFT Festival of Learning. Please welcome Professor Joe Paradisio, who will speak to us about research from his group at the MIT Media Lab, the Responsive Environments Group. So Joe Paradisio is a professor at the MIT Media Lab, where he leads the Responsive Environments Group, and he is also the academic head of the Media Arts and Sciences program, which is the academic program at the MIT Media Lab. But prior to that, Joe started his career as a physicist and was at CERN. And afterwards, he had has an illustrious career in creating sensors for various types of applications, from smart homes, smart buildings, to wearables, to even systems for artistic shows, like with the famous magicians Penn and Teller. Joe is also an amazing musician and music aficionado. And he's actually enjoying being in Paris for some amazing French prog rock and jazz concerts. But aside from that, Joe also combines his interests between electronics, engineering, and music to create his own massive modular synthesizer. So I won't give too much away of what Joe is going to talk about. Please give a warm welcome to Professor Joe Paradisio.
Thank you very much, Xiao. It's such an honor to be back here at Da Vinci. It's always great for me to come and see the inspiration of what we have done at the Media Lab, brought by people like Xiao and Mark, and really have it ingrained into a lot of the projects and the style of which the students really innovatively approach problems. So it's just so inspirational to see this take root here. And it's always so much fun to come and work with the students. Some of the students even come to work with us at the Media Lab. And Tomas, of course, just spent a few months with my group working on a wearable for sensory augmentation. And it's just so great to have this connection with you guys. I always love coming. So I'm going to talk about a few things. How many people were at my talk I gave a year ago at the inauguration ceremony? Quite a few. So I'm going to touch on some of those things, but this is a longer talk, so I pulled it. And there's going to be more detail, more projects. I'm going to give you guys more of a tour on what we really do. This is the structure. So I'm going to talk at least in the beginning a little bit about the Media Lab, because again, that's one of the big connections between Da Vinci and MIT is the Media Lab, where they both meet. So I'll talk a bit about what it's like there and why we do what we do. A bit about me, and I pulled that into a longer segment where I'll kind of talk about how I got to where I am. Xiao summarized it, but I'll highlight a couple of things on the voyage, including the music part. And then I'll talk about stuff in the group. So I'll go from wearables to sensors diffusing into materials, stuff we're doing with augmented reality and what we call cross reality, where sensor data manifests in virtual worlds. And if there's time, I'll talk a bit about extreme sensing and other sensors. So this is the Media Lab. It's a wonderful place. Glass building, a lot of light comes in, very open, and open in many ways, not just physically, but also to exchange of ideas. Very different kinds of groups in the same quarter. Every PI is an expert in the areas where they focus, but we have lots of collaboration between ourselves and with the students. So we're really free to imagine different futures and build them. It's all about building, making a piece of this future, giving people a taste of what this future is going to be there. We respect theory. It's important, but we emphasize building. So you really want to make a piece of this. And yeah, you want to analyze it in the proper context and see what it points to, but show us what this future is like. We're very disciplinary, as I said, even within an individual. I'm very motivated by music. I love physics and did my work there, did spacecraft control, and now I do sensors and human-computer interface. So you tend to see this blend of interests even within individuals at the lab. It's electric because of this. I've worked places where you can close your door, nobody disturbs you unless there's a crisis. The Media Lab is impossible. There's always people visiting from different groups, the students that come with ideas or that are asking for advice on a different project. You just can't wall yourself off. So you're always barraged. There are member companies coming from different industries. It's a very electric place. So opportunity abounds. this is a list of all the research groups at the Media Lab now, all with different expertises. I'll highlight a few. Of course, there's me, and you'll hear a lot about what I do here, you know, sensing and applied to all different kinds of connection of people to the world of data around us. Patty Maz's group is very close to my group. They're our neighbors, but the students work back and forth quite a bit. She also spoke at the inauguration. Some of you people saw her talk. She is about kind of the interfaces to the brain that aren't necessarily invasive. So a lot of work with sleep, a lot of work with trying to sense intent before you do it. It's an interest that's been developing in my group too, so there's a lot of collaboration back and forth. Hiroshi Ishii, where Shao did her PhD, a very close friend and colleague, also spoke at the inauguration, really about making the interface physical initially, but now really about materials that actually can be active, that can be controlled, that can change their properties dynamically, and trying to think of new interfaces between this world of information and people using these kinds of things. So he builds the materials, as we do in my group a little bit, but he also works a lot on different interface modalities. And then you have Jenna Dagravarian. She's kind of getting a bit more toward a strictly technical area where she does soft electronics, stretchable electronics, but she applies them to wearables. I found her, I recruited her for the Media Lab when I saw a talk she gave about harvesting energy from a beating heart by putting a piezoelectric element in there. So I did a lot of energy harvesting in my group. I was fascinated by that application. I brought Janet in, and she's doing a lot of work now with arrays of piezo elements, for instance, on the skin to start to image inside. She has a bra that she's actually made for women's health, so you can put on every day and just check for breast cancer. So every day you have something you can compare to, and it's just something you put on, take a measurement, take off. So she's got lots of projects like that that are exciting. And then Hugh Hare, biomechatronics, putting a robot physically on the human. So he works with people that have had an injury or that are physically disabled. If you augment somebody with a robotic appendage or robotic prosthetic, that prosthetic has to learn to walk with the rest of the body, if it's on the foot, or to move with your intent. So some of it comes just from motion artifacts from the parts of your leg or your arm that can move. Some of it can come from EMG signals. Some of it comes now more and more from AI interpreting those to figure out what you really want to do. And eventually we have the direct neural connection, so you can make it be part of your body. So Hugh looks at that whole constellation. And we have a project now, we're working together for magnetic space boots, right? We're doing more and more space projects at the Media Lab. Large space habitats will happen. Who knows how long we'll be using them, but they're going to go up. People will have a lot more area and space in these big enclosures. So we have to rethink restraints. Right now, astronauts fly from place to place by jumping. There are moments maybe when you can walk like in the science fiction movies. So using knowledge from prosthetics so that the motion of one foot can affect the other, anticipating gait, learning gait dynamics as you begin to move, instead of having a switch to pull it off or having to pull your foot off, it anticipates how you walk. So it'll be releasing as you move. So it's just a great collaboration, the kind that can happen really at the Media Lab. And it's a student from ETH that's visiting me that's doing the work in controls. So it's really a great collaboration. And then, for example, Mitch Resnick, he is the guy that developed Lego Mindstorms. You guys probably know that, the first robotics kit for Lego. Then he went on to develop Scratch, the programming language that's taught probably several of you how to program. That came out of Mitch's lab. So he's all about kids and computing and education and epistemology. Drilling down to another group, Devlina Sakar's group, Cyber Nanobiotech. I've gotten very close to her work now that I'm academic head, and I love it. Lots of interesting projects, but one of the real game changers she has is looking at electronics for the brain, for example, that you don't necessarily implant, right? There's ideas of brain-computer interfaces where you put these wires into the head and you have microfibers that go down. Very hard to do. It feels almost destructive, and they do it, for people that maybe, will have to move a prosthetic arm, but they tend to have to take it out because it doesn't work that well as a permanent installation. But why not inject these things into the bloodstream as nanoparticles, have them actually find with a bioreceptor on them where they want to go, including in the brain, and then send them commands with radio or magnetically to have them activate. Or maybe interrogate them, and depending on what happens there, they can send a signal back. So her work is of that sort. She's winning all kinds of awards, really looking at the edge of what human-computer or brain-computer interfaces would be, including things like working on brain tumors. For example, if you have a tumor and you have a magnetostrictor, the magnetostrictor can attach to the tumor, and if it vibrates at a certain frequency, which you can do just by sending magnetic signals in, it can disrupt cell division and actually begin to eradicate the disease in some cases, right? So it's early, but it's incredibly promising. She's getting all kinds of awards for the work. My colleague Fadel Adib, he is one of the fundamental people at MIT that did the Wi-Fi wireless sensing. Some of you have heard about it, where just with radio, looking at multipath and reflection from the human body, you can figure out how you're moving, certainly see where you are. You can look at arm motion, but you can actually look into the body, see people breathe, and see the heartbeat. So he did that as a grad student with Dina Katabi's group, came to work with us, and he's got lots of great projects looking at low power backscatter tags that take very little energy, but they can measure something. Just send a radio signal to it or an acoustic signal to it, and depending on how it changes its reflection, you get the data coming back at very, very low power. As well as a startup he's done that came out of a project in his group. He's doing the startup now, where he's got augmented reality glasses on people that work in warehouses. You have RFID tags in the boxes that signify different kinds of items that may be inside. If you want to look for them, you have to now look it up, find a barcode, see where it is. Here you can just put the AR glasses. It can read directly with antenna on the glasses the tag, figure out where it is as you move, and show you an indication in AR where that tag is. So you're looking for something, you can just see it in AR. So one of many great projects he's doing. This is from one of the last member meetings that we had when all of our sponsor companies come to join us at the Media Lab. We all had workshops. You can kind of see some of our interests. Smart materials, I'm working on that. Hiroshi's working on it. There are a couple of other groups interested. We had a whole session on sensing electronics, actuation of materials, new kinds of materials for that. AI and future of work. Digital currency, we have a group looking at that as well. Creativity with AI and other things coming down the pike very quickly. How does that change creativity? Whoever guessed AI would hit creativity so early? Just incredible, right? 10% the synaptic density of the brain, more or less, you can do all this stuff. These machine neurons are different than ours. They can do some things better than us, and they're tackling creativity, right? They're making art, they're beginning to make music. Who knows, right? It's the early stages. This is going to explode. We didn't think it would be here this early. Extreme sensing, that's a lot of what I do, but also Ramesh Raskar is about computational photography, so on and so forth. So lots of different interests. They're all coming together at these big meetings we have. This is a chart I built to kind of describe the Media Lab back in 1998. I've been there for a few years. I saw how it worked, and it really is a collection of all these different interests and expertises in the different groups. These are some of the things we were doing back then. We're still doing a lot of them now. The world has moved on. But they would be kind of mixed up. It wouldn't be any kind of an organization. This group does exactly this. This group does exactly that. There's a lot of blur between the edges. And the students were kind of the glue that held them together, right? So students take classes from other faculty. They work on each other's projects to some extent. And the information just travels in these different domains across the barriers by the faculty talking to each other or the students working together. And then we have all the member companies coming in that just go on tours, one group, the other group, the other group, and they pick up and leave information as they go, kind of like bees pollinating. So it's really an ecosystem of very, very diverse interests that actually does work and makes it very exciting. So this is about as close as we can get to an org chart. You probably can't see that in that small screen. But the lab was set up in the mid-1980s by Nicholas Negroponte and Jerry Wiesner to look at what Nicholas called then convergence. He's the guy that made up that term. When you had computers basically taking print, publishing movies, music, and bringing that all together into one platform, right? So it's going to change the way we really deal with media. That's why we're called the Media Lab, because this new platform, this computer, which is going to be everywhere, is going to integrate all these things. And indeed, he's right. We'll talk about that in a minute as to some of the downfalls of that. But it happened. And then we move more or less to Internet of Things. So atoms, bits, people, how that comes together, which really people call now more or less IoT. We're very, very early players in that at the very beginning. I've done a lot of my work in that area. And then we talked about, and probably to the current day, it's really body, brain, and technology, how these all come together, right? So how does the mind, the brain, and the body connect to all this information? How does it go back and forth, interfaces to all of this? My colleague Neri Oxman made this Krebs cycle to describe us, where you have Krebs cycle is how bacteria basically metabolize and recycle nutrients. She was thinking about how ideas go through a similar cycle at the Media Lab. And if you look at the different axes, you've got science and engineering, right? Engineering is kind of applied science. You can, some universities even call it that. And then you have art and design. Same kind of analogy on either side. The Media Lab kind of bridges all of this with convection. So, you know, a lot of us come from science backgrounds. There is science happening at the Media Lab, and certainly deep engineering. Our engineering is as deep as anywhere at MIT. But then we have the art and design aspect, which is unique, that it comes together. Most places keep that separate. At the Media Lab, we embrace it, and students and ideas go across that boundary. She has another version I discovered that people forgot about. I just found this in an old document, so I took a picture of it. And she was thinking more broadly. So the outer circle is still what I showed, but then she has, you know, metaphysical and you know, some of the group names in here, but it gets a bit more philosophical. But again, same kind of idea. Lots of different approaches to solving different problems or approaching different challenges, which is what makes it great. So now switching over to me. This is me as a, oh, how old was I? I was probably 15, 14. I was 14, I think, maybe 13, when I won the science fair back in the 9th grade. I was a local in Boston. Somerville's a suburb. And I was doing sensors already back then. It's what I do now. It's kind of what I did then. So this is the days of the first space age in the US. I was always building things. Then I did my PhD in high energy physics, actually, at MIT. I did my PhD at CERN, but that's not CERN. I know one person who knows what that is. Does anybody else know what accelerator this is? It's a bit further north. This is the Petra E+ E- collider at Daisy in Hamburg. I think it's gone now. They took it out to build part of Hera, I guess, the next collider. But yeah, that's where we also had an experiment. So I spent my first months in Hamburg, first time I was in Europe. And that's me as a very young MIT grad student, working with Sam Ting's group, who had just won the Nobel Prize. That's my experiment at CERN. So the intersecting storage rings, 62 GeV, it's more than 2 orders of magnitude less than what the LHC gets. So it was the highest energy at the time. It was, what, a half mile in diameter, something like that, 3/4 of a mile. Francois would know. But yeah, this is what a big experiment was back then. And there's Professor Vannucci, who is also here right now at the old experiment, my old collaborator from those days. I think that's you, pretty sure, a young Francois. And that's another view of the detector. And of course, I love photography. You know, the artist in me did not want to die when I was there. I had to have any kind of outlet I could to have artistic expression. I was always taking photographs all my life. So that's the time exposure by the old cathedral in the old town at the top, the archives. This is taken just a year ago by my daughter. So same place. Although you can't get the time exposure so easily with a phone. This is during the same lighting conditions. It seems like it's day. Incredible how technology has moved. I got a little older. And of course, this is so important for me to bring my daughter to Geneva and show her the things that were very important to me. So that's me and my daughter Mira with the chateau in the back. And this is at the Atlas control room. So keep a good relationship with your kids as you grow older, because it's the most important thing in your life as you age. I think most of us that are having gray hair realize that. So it's just so great to do this. So going back to CERN, that was my old CERN office. So that was the door. I put crazy pictures up. That was my desk. I was into making computer graphics already back then. This is my desk at another time. You can see I was already a Magma fan, famous French band back then. Desk a little later. So this is the desk at a different time. This one I was into photography. And that's when I moved my office. So I had to clear everything out. So yeah, that was my life for 2 years. And there I am in my CERN office, and there's Professor Vannucci over there trying to hide with one of his preprints. But they were great days, amazing days for me. And of course, the first place I really lived in Europe was in France. So that was in Saint-Genis. That was my old apartment in Saint-Genis with all my work at CERN kind of laid out there. Then a postdoc at ETH in Zurich. working on one of the central detectors for one of the LEP experiments. And that's me as a relatively young man with Zurich in the back with ETH Centrum. That's me and my daughter, same place, right? The town hasn't changed so much, different world. That's the time exposures, same area, same place. Those lights are all gone now. I used to love all the concerts. Already then, I was going to concerts all the time here in Europe. So Zurich had a recommended records store, and they would bring all kinds of amazing avant-garde acts. I would go to the Rote Fabrik all the time. It was just a great moment in Zurich for music. With my office at ETH. So pivot on to music. That's the technical arc. Music, as you heard from Shao, very, very important to me all my life. So I just grew up, and for me, life is not worth it without music, right? It's one of the most important things that really speaks to us, that keeps us going, that is a fundamental part, I think, of being human. And how will AI take over music? I think it will. Will it appreciate it? This is intriguing, deep questions. We can talk about it in the Q&A. We're working on projects kind of like that at the Media Lab now. But yeah, for me, it was very important. This pile of records turned into many, many more. For instance, this is me just a few days ago. This is a story I used to come to in Paris in the 70s. It's still there. And the CDs are €8. Obscure French jazz, crazy avant-garde rock. I still collect it. And I'm driven, for me, it's like research, right? Research, you're looking for something new, to do something no one's done, to find some piece of information that people don't know. For me, I quest music the same way. I want to find music I've never heard, that few people have heard, and let me bring it back and expose it as I can. So I've donated all my CDs to the Internet Archive. It's a spin-off of MIT, actually. Bruce Dekel is an MIT alum. He believes in keeping all of the world's information forever. So as you know, it's the Wayback Machine, but he's digitized books, gets in trouble for it because he lets people read them when he shouldn't sometimes because publishers don't like it, but also music, records, vinyl records he rips, but CDs. So I gave him 18,000 and plus rare CDs I collected all over the world, and he's digitized them. Of course, I digitized them myself before I gave him the CDs. But he scans the liner notes. It's all there preserved. So all the stuff I collected all over the world is there. You can always go and look. And there's a lot of crazy music. So yeah, when I was growing up, the sounds I heard on the records I could get, especially the ones that had electronic sounds in them, were very important to me. So these old tape music records I would get for just a couple of dollars. I loved the sounds that were on them. As a technical kid, I wondered what would make these sounds. And then you start seeing pictures of modular synthesizers in the early records like Switched On Bach, the first record that broke the Moog synthesizer to the general public. Wendy Carlos doing Bach on this, and very careful renditions of Bach, but definitely electronic sounds. For me, what the hell is this thing behind? I thought that was Wendy Carlos at first, but no, that's supposed to be Bach, I guess. But this piece of gear, what the heck is it? So I found out. I learned over time, and then when I got these records, I mean the German electronic music scene of the 70s really gave the synthesizer its proper sound in popular music. So then suddenly, they wouldn't just be boopy bleepy, there would be bits of that, but there'd be these beautiful atmospheric soundscapes that they would create. Tangerine Dream, Klaus Schulze, Ashra Tempo, we all know these bands, some of us do. For me, this was pivotal, right? I love this, I wanted to do this. I wanted to make this kind of music myself. And of course, to have a modular synthesizer, they were incredibly spectacular. Musicians would go on tour with them. As a kid, I could never afford to buy one. Back then, it was $10,000 in dollars of 1970. Incredible amount of money now. Modulars are cheaper now by comparison. So I could never afford it. So I had to build one. So I learned electronics, and I started building my synthesizer in my parents' basement. So this is me just learning electronics when the linear catalog from National Semiconductor was the tiny book, and designing and building all these things. These are some outtake photos. There was an event at Tufts I was dressed up for, so I figured, okay, I'll post with the synth. I'm glad I did because there are very few pictures from that time of that. So this is music I made on it in 1976 when I first built it. The one cabinet. Let me turn that up just a little bit. You can hear it, binary counts are making that sequence is going. I'm playing an organ, I'm going through all kinds of processing in my synthesizer, taking the sound. And at a certain point, I have the sequencer coming in. So again, I was going for that kind of early Berlin, Klaus Schulze, green sound. I kind of approached it here. You know, my version of it as a kid. I was just turned 20, I think, when I was taking it. And this is the sequence we're coming in. So I built a pseudo-random sequencer, but I could tune it up. So it's just playing a riff, and I could hit switches and change working sequences. Then I went to Zurich, of course, as a postdoc. And after working like crazy in the lab on our detector for a year, I had to do something else. It takes a while to break into the culture in Zurich, meet people, and do stuff. After 2 years, I had a lot of Swiss friends, but it took a while. So I had to do something with my time. I had all these ideas for synthesizer modules I could build. So I went crazy just building them. And this is me in my apartment in Zurich with all these synthesizer modules. And this is it, what it became after I came back to the States. This is in the MIT Museum, set up in 2012. I do these big installations of these autonomous patches. So this thing is just dreaming its own music. The programming is coming through the patching. It's an interface we forgot about when we went to digital-driven music. But this is what, you know, Shao and I know is tangible interface. It's a physical thing. Your hands are on the cords, on the knobs. Different relationship you have with making the sound. And it's a totally different feeling. It's exhausting to work with it, but I can do things with this system that I can't do as easily with the digital system because I'm immersed in it. It's there. It's physically distributed around me. Different experience. You can see kind of the way it works, right? Logic in it here, mainly. So all the wires are kind of connected. The patch cords are connected around where the logic is. The ands, the ors, the flip-flops. I'm basically building a processor dynamically by patching that's creating this behavior that you're hearing here. So it's triggering sounds, it's changing them. It's causing different effects to come in. You can crank it a little bit, actually. Having the computer opened up this way gives you access to all these intermediate signals. You can grab bits that are being used for other things, use them in a different sound, use those to change another sound. It's totally cross-connected. So it's, you can build these sonic worlds that really are amazing to explore. That's how I see it, exploration. Building a world that I'm exploring. So this is another one. This is what it looks like now. It's in my studio at home in my house. It's in my basement. And I think there's a... there was a patch here. I guess you may not hear it. But it's streaming from, it was streaming from there to Zurich actually for an event that was happening at ETH. Again, it's getting bigger. I'm still adding to it. I'm going to take a sabbatical next year specifically to focus on this, to see where this rabbit hole is going to go because it's got a lot further to go. This is, I think I showed this last time I was here. The last big patch I did about a year ago. And it's just again, dreaming to itself. Hundreds and hundreds of patch cords, lots of complexity, lots of sound, just an incredible environment to work with to make sound. And it just evolves and changes and goes into different modes. I'm not touching a thing. It's just kind of dreaming to itself. It's a connection as a network, not done with an AI, but done with physical patching. Right? So it's living at a much simpler level. It's got all this complexity. I'll talk about it in a second. We did a workshop from my group in Fribourg in Switzerland about smart buildings, but they have the world's greatest synthesizer museum there. It's a warehouse in the old Feldschlossen factory, and it's just filled with thousands of keyboards of every kind. There's a crazy collector who just kept collecting them, donated them all to this place, and they added more. To walk through that and see all this gear from the 1960s. They even have a Hammond Nova chord from the 1940s, the first synthesizer, all the way to things that are newer. Just an amazing experience. And I gave a talk there just about the synth. If you guys are interested, they did do a great job posting it online. You can search Joe synthesizer SMM and you'll find it. So that was the prelude. Now moving very quickly on to the work I do at the Media Lab. So we work at different scales, from wearables to smart buildings to smart landscapes, environmental sensing, and now more and more to space, projects that actually we do deploy in space. I'll try to cover quite a few of them. This is the group at different stages. I have anywhere from between 10 and 20 students. I have a lot of visitors that come from all over the world to work with us for some parts of the year. MIT students I have on the order of about 10 right now, 9 or 10. But it's a great group of creative people that have all different kinds of backgrounds. So wearables, the Media Lab is the place that really gave the name to wearables in many ways. We had the big evangelists in the beginning of wearable computing at the Media Lab, namely Thad Starner, who kind of went on to make Google Glass, and Steve Mann, who's a pioneer of everywhere augmented reality. And they had many acolytes, students that would just figure out how to wear a computer already in 1995. They would live their life that way. Thad was living his life with wearable augmentation, with a display and with an interface and wireless connection already since then. Steve was wearing TV cameras and displays since that time as well. So the stuff we're grappling with now in products, they were basically living with it in those days. And we had a symposium on wearable computers and a fashion show and stuff like that. So we all thought of things we could do for the symposium and for the fashion show. So I wrote a paper for a symposium and did an installation of a fashion show on a shoe for a dancer that had sensors in it. We did about 16 sensors per shoe, wireless right from the shoe to a computer, a rule-based at that point in the computer that would take the sensor signal, map it, and use it. And the dancer could just dance, and you'd hear the data in real time. So we demonstrated this at the fashion show for the Wearable Computing Symposium, but also showed it all over the world, including here in Paris. In 2000, we ran it in the all. So yeah, the rate gyro when he spins. When I would talk about all these sensors back in 1997, it was black. Now it's just, just walk past most of them. It's a different world altogether. That's sonar. And then we went on to work with wearables for extreme sports. I met the doctors that do sports medicine. We developed a gait analysis system for them to analyze how you walk. Just a wearable sensor node for the foot already around 2002. And then they introduced us to the doctors that attend the famous Boston sports teams, the football team, the Patriots, and the baseball team, the Red Sox. So we go down every spring training, build these sensors for the athletes, just strap them on and measure what they do with their hits and their swings, and then analyze it after with the doctors. This is, again, middle of the 2000s. Very early for this. No one was doing it really with these extreme range sensors because they throw at 120 Gs or 10,000 degrees per second. You have to have the range to take all of that as well as slow motion. So you have to get all of that together and then fuse the data dynamically. High bandwidth wireless interface to get the data back at kilohertz. Full sampling on all the nodes. We weren't baseball fans. So people, they come back. We come back, people say, did you see this player? Well, maybe we did. We might have had lunch with him. We don't know. So they appreciated that, actually. Then we moved into sensing to really detect things that are more intrinsic, like comfort. Hard to say how you measure comfort, but you can start to infer it if you get the right kind of measurements and the right kind of processing to try to reduce them down to things that really do begin to read on comfort. So one of my students around 2008, 2009 developed this very low-power wearable for smart HVAC to control the heating, air conditioning of a building. Instead of with the temperature on a wall, you now have temperature measure at the wrist, but you can ground it by saying you're too hot or too cold. So you have buttons that you can push to basically tell the system if you're comfortable or not. It would take all the sensors here, including motion, knows how much you're moving, knows where you were before. It knows, again, the temperature where you are. It has temperature sensors also in the environment it uses in the wall and then outside. And it builds a model of whether to heat or cool based on whether you hit hot or cold. So it can predict. So it's predicting comfort in that sense. So the red is too hot. This is where the person said they were too cold. And then the machine learning model, a very simple one back then, would do a switch curve. You can do much more now with AI in this. Actually, I'm talking to you guys about projects that we're looking at in this space. MIT takes it very seriously. Wearables, environmental sensors, and AI to do the prediction and do the modeling. So we're living in a different era. This is a system we did to control lighting. So that's my student Nan Zhao with Google Glass, and it has light sensors in it. And she's in an office, and as she does different things and moves around the office, the lights all change. So she's getting always the right amount of light into her eyes because it knows how much is coming in. And then it can tell she's being social. She's on the phone. It detects that. It changes the light into a warmer tone, conducive to being social. So she gets off the phone, assumes she's going back to work, and then a colleague visits. Most of my students back then were musicians. So Gershon comes in to serenade her a little bit, I guess. And it senses that she's in a social mode. She's talking, different kind of motion, and it goes into the warm light. So the light switch is going away, right? It doesn't mean anything now. What does it control? There are whole settings of lights. You can go between different settings. Can you actually string them together in principal axes that reflect human preference and then control along those? And that's where this work actually went. And went further, taking whole environments. I think I showed this one at the last conference. So could you bring a library, for instance, into your space if you wanted to work and focus? More than that, have it automatically determined by wearable sensors that can detect if you're stressed, detect if you're focusing on work or not, and try to bring the environment into a mode that would help you. Everybody is different that way. We react differently to different stimuli. It can learn by seeing how you react to different things we put up. So we did this. This is a simple proof of concept, right? Someone has a lot of time on their hands, but now he's relaxed in his office, but now he has work. So he's stressed out. My students are great actors. And here, everything worked, but we didn't close the loop. So at the beginning of this, we showed an open loop system. The sensors are detecting stress markers. And the classification worked. We tried it on many subjects. We could tell if they were being stressed out or if they're restored. So for him, the woodland setting is a relaxing one. So it changes the room to try to get him centered. It then detects he's going back to work. We can actually look at head angle, look at respiration, look at heart rate variability, all of this. So it fades the room into a setting that's better for flow for him, which in this case is the library. So now ideally he's relaxed and productive, right? The room is a partner to try to keep him in the right mode. Not only anticipate what you want to do, but anticipate what your state is. This is a closed loop system, actually looking at reweighting different images. This is focus restoration. It wants to be in the blue state. She's here now. It keeps changing images until it gets one that brings her closer to this. This is a portable version we did with Steelcase. Steelcase are sponsors of the lab. They've been with us for years and years. They gave us these portable workstations, and we augmented it with our system as well as scent displays, thermal controls, and then we had lighting up on the top. So we could do even a little bit more than we did before, but you can move it because it is dynamic and you can take it more or less wherever you want. So Steelcase made about 4 or 5 of them, brought them back into developing projects and ideas around this there. And then we thought about sensors for safety, again, early 2010 vicinity. For workers, because you can make a dosimeter for a worker that can measure different kinds of gases they encounter, as well as see how they're moving, look at temperature, lighting, all these other factors, sound levels, and then try to back out what different work environments are for different people. Maybe even flag signs that could be alerting. This was for ENEL, the Italian energy company. They were refurbishing nuclear power plants in Slovakia, and they wanted to think about a way to monitor worker safety. Big news now. You start seeing products. Back then, this is very, very early. You can even see the particulate sensor is so big, it gets tiny. So here's a video display that shows a worker here. We can tell if the worker moves, see the accelerometer move, we can detect who is who. So we can look at, for instance, the height with the barometer. If he's too high, we can flag it as red. So in the video, you start getting information back to the user. And the background is actually colored with the gas. So if there's more organics, I think it's yellower. If there's more ozone, it's bluer. So through subtle alteration of video, you can start giving this information from the wearable sensors back to people that would want to monitor workers for safety issues. But then my students would go to Shenzhen in China every year. They even went this year. MIT actually had some special arrangement. We could let them go now to Shenzhen. It's an incredible place to send students because it's a manufacturing hub like none other, right? Lots of the world's stuff are manufactured and prototyped there. It's a city built just for this. Some of you have probably been to Shenzhen. But bring the students there with people that know the ecosystem, bring them into the factories, talk to the integration engineers that tell them how to get things manufactured at scale. It was transformative. So students would go usually with some idea. They would learn how to suddenly spin up a production and really make it. So it was just incredible. And this is what came out of one of these trips. You saw in the mediated atmospheres, we had the room change because of the sensors. There were, a chest strap, there were watches, there was a camera looking at you. Could you start to do some of these things just with glasses, right? Because they have access to various parts of the head. They can look inward as well as look outward. Can we start doing things with glasses to get some of that data? So, and of course, it's known that things like difference in temperature between the bridge of your nose and your temples can relate to cognitive load. So there have been studies It's a noisy measurement, but the effect is there in Stroop tests and tests that stress people out and load them differently. You can start to see an indication of cognitive load just by measuring temperature here. This is with a thermal camera. But you can do it with thermopiles as well. So we put them in the frames of the glasses, measuring temperature at the temples, measuring there at the bridge of the nose, and then other sensors as well. So we can look at how the head moves. We can look at eye blinks. We're actually getting sensors now look at eye motion, ways to do that too. And lots of other things on the thing. And it can light up in different ways. It can be an output device. So this is some of the data coming from it. It's basically working. It's seeing how your head is moving, eye blinking, temperature is there. Some indication that we could be seeing the beginning of cognitive load. That needs more work. Has to be grounded, I think, with other sensors. But there's signal in it. We do get the temperature. But my student Patrick went even further and built an array of sensors up above the ridge of the nose to measure air quality. And it's incredible how small air quality sensors get now. There's a whole suite of them. You can see it kind of close up here. You can see what it measures over here. And we're adding a particulate sensor. There's a new sensor coming out from Bosch. We have special early access to it. It's PM 2.5, but it's tiny. It will fit right in there. So you measure the air you breathe, basically, right in front. So we developed it, and we started doing collaborations around the world. We have a student coming from the Smart Living Lab at the University of Fribourg. The Swiss take building science very, very seriously. Some great work happening in Switzerland, I'm sure, as well as in France, but it's a big national initiative there. So she came to work with us for almost a year, built part of her thesis around the glasses, and then brought them back to Fribourg as well as to Singapore and did studies in buildings to look at what people are exposed to and also how they were affected by other things, because we can again measure things that relate to affect as well with these. This is one example looking at how distracted people can be when they're comfortable, right? If they're comfortable, they're not too distracted by things. We have an intervention that comes, the glasses can change color or can vibrate. When do you notice it? And they don't notice it very much, whereas if they're not comfy, they notice it more easily. Statistics, of course, could be better here, but we see a signal that really looks like there's a difference. And then sensor focus. So this is all kind of leading up to that, right? Can we measure focus? Can we measure flow? And my student David Ramsey was deep into this. Again, we're at fault for this because the Media Lab made this computer really the flagship institute set up to pioneer it. The world built this out, but the lab was the first place that articulated that this was going to happen and started building projects to really poke at it. So yeah, when all this comes together, Xerox PARC as well poked at it. This was happening. Research had it. We were like a lightning rod for it. But damn, I keep losing my track here because I'll get an email from somebody else. There'll be some post or alert from this or that, or I may want to look and buy something on eBay or Amazon. This platform is just full of distraction. Nothing is keeping me focused at all. It wants me to fraction out. And this, I think, is one of the big issues that we have to grapple with in our current day, because this fragmentation is a problem. David built a bunch of platforms to measure this. The glasses, again, they can give you interventions that you can see. For instance, here, it can change light on your peripheral to change a color from blue to red. And you can just touch a capacitor point or touch something on a watch or another device if you notice the change. So that's what we did in the other study. You see this change. If you're more engaged in flow, you're less likely to notice that. So could we measure this? He also built a watch. I said, David, why are you building a watch in these days where you have all these great digital watches? He built a watch that doesn't tell the time until you guess the time. And that's kind of intriguing to look at time distortion. If you're engaged in something that you really are totally immersed in, you don't notice the time pass as much. So you have to guess it with a slider before it tells you the time. And another one that pokes your leg, and it pokes it ever harder until you notice it, and you have an app on a phone or something that you tell you notice it. So different ways of putting people in different experiences to look at engagements and measure it with devices like these. And he did see signals with a watch. Yeah, people did have distortions of time depending on what they're doing. They would catch up because they would normalize, realize they were working on a different time scale. This is the color shift. He did some studies himself, like we did with the people in Fribourg and the leg vibrators. So. He also instrumented his life, put his life online in 2023. And he had the whole concept of, can I be immersed in things that are all convergent as we are now with modern devices, then make them just segmented, right? He would get his text on a label printer. He would not carry a phone, gave up his phone. He would be able to do email on a pad that could only do email, nothing else. Things like this, really segregate every part of his life. And he would measure himself with the glasses and other sensors while he did this. So this is David talking about it. Can you crank it? Turn it up. Is this working? Do you have audio at all? You should, unless this gave up. Well, he's talking about what he's doing. It could be that the interface decided it didn't want to work anymore. I can plug it into the regular. Can I pull this out? Okay. Let me. I don't know if I'll this is David saying essentially what I just told you, so I don't know if I'll go back there. But let me go to sound here quickly, and here it is. Where's control? There it is. Let me go to that. Okay, I'll go back. Now,
capture and share.
That's interesting. It doesn't realize something is plugged in.
Video of my room, my face, and
Did something
every one of
unplug?
my screens as I'm doing all my activities, and stream it live
Weird.
on Twitch as I do it.
Very weird. I think something gave up in your connector. Yeah, I can do that and put the microphone by the speaker. Don't have too much time left. But hey, he gave us his phone for that. Old-fashioned phone. He's an old-fashioned guy. Okay, good.
Hello.
Okay. And going on to wearables, did a lot of work in my group with energy harvesting, thinking about trying to get energy as you walk. We did pioneering work back in the late 90s on this. But we thought going further about powering mobility. So this is, if you want to get mobility, rather than harvest energy, you can hop onto something that's moving and hop off later. This is a sensor node we built already back in 2005, looking for light. It hops onto a host, which was the person, hops off when it sees light. So it hops onto things that are moving, hops off where it wants to go. Here's a node that will stick like this. That's like a flea or something that will hop on, right, to someone that's nearby, hop off somewhere. This is like a burr, so it sticks to the most recent object. And now she's transported it to her chair. So, and it will stick to the chair because the chair is more recent. So she's transported the node. And yeah, if it's flatter, here it has a pager motor. If it sees light, it shakes off, it goes away. So we can think of sensors traveling on the backs of moving agents, including people, to get from place to place. So we started thinking of robots that could actually crawl on people, move on people. This moved quite a bit further with the Rovables project. I don't know if I showed this in my last talk, but my students started to think about robots to navigate on clothing. So wearables that are dynamic, they don't stay in one place, they go to where they may be best suited. So here is a wearable crawling up the skin. And so they're where they want to be for motion capture. So they crawl down to the sleeve. Here's a wearable looking at where a watch wants to be, or a display on the wrist. It needs more space. It finds a neighbor and can have more display space. This is some poker. I don't know exactly, a notification or something. Jewelry that can move. This is work that Cindy Cow did, one of the other students at the lab. You get a call, you can have the microphone come up to where it's best placed. And again, we could navigate and find their way across clothes, lots of different algorithms to do that. And then I told Artem, rather than think about crawling on the clothing, and I was trying to think of what is that good for? It's good for a few things, but it's hard to get a good use case. Crawl on the skin. So he built a set of robots that could crawl on the skin using pneumatics or using flexible robotics. And you could put payloads on them, for instance, a camera to image. You could have measurements you could make as well with electrodes and so on. You could even have a needle to do targeted therapy. And he made it eventually light enough, found right motors that it could be untethered. It had trouble moving, but the pumps have gotten even better. So we could start really thinking about robots to move on the skin for telemedicine, where you can't get a gantry robot. Robot can go and find something wrong and do some therapy or diagnostic tool. We published that in IEEE EMB, the Transactions on Biomedical Engineering. It got the cover. So they liked it. And of course, I did, after high energy physics, I spent a career working in spacecraft control with Draper Lab. So I became a rocket scientist for a while. I thought I was done with that when I went to the Media Lab, but no, space is much more accessible. We started a space initiative, and we started flying things in zero gravity flights and getting things into space very quickly. It's very easy to levitate actually in zero gravity. So one fun thing. We just published a paper in IEEE Pervasive last year on projects we would start in ubiquitous pervasive computing, more HCI type work, but moving them to space applications. So I'll give you a couple of examples here. The little robots that crawl on clothing, we made a fleet of them to crawl on spacecraft. So they can actually go on the outside of a spacecraft and diagnose what may be wrong, and make a measurement, take an image, or do something, maybe even do a simple repair. If you can't get a robot around to it, you can just crawl along the edge with one of these. So we've put different sensor payloads on them, more suited for structural analysis, and flew them in zero gravity. So you can see this in zero G flight, looking at different modes of locomotion and attachment. And of course, we can think about getting things to the moon now, right? Moon is much closer. These were all the missions that went to the moon, all the landers before the last year or two. It's just exploded now, right? We almost landed on the moon. We did land on the moon with the IM lander, but unfortunately it is at an angle. We have a payload, which I'm going to talk to you about now on the next one. So I'm hoping that one lands vertically. They learned their lesson. Better always to be on the second mission, not the first. So yeah, this is the little rover that's going to go on top of that lander. It's by a company that's a spin out of MIT, and we have space on it. Nokia is the main payload. They're going to fly actually a 3G radio there and start playing with 3G on the moon, more or less to say that we've done 3G there. It's going to be on the lunar south pole. Yeah, again, kind of where the other lander landed, or more or less landed. This is what we're flying. It's one of the micro robots, again, designed to be a diagnostic for the bigger rover. So it's going to measure the heat capacity. The top face of this is a heat shield, or a thermal conductor, a radiator. It's going to measure the position dependence of the thermal response. It's got a little thermal pile down below. So when it lands, we'll open that little garage, and it'll come crawling out. Hopefully. Hopefully, vertically. So that's the thermal pile. This is a charging port. It's all space qualified motors. We ran it in a TVAC test. It's got a little heater so that it keeps the right temperature. This is a breakdown of the whole thing. And that's it crawling out of the TVAC chamber that we have at MIT or Astro. So we space qualified it. And every great voyage begins with a FedEx package. You can't FedEx to the moon directly, but we did send to the integrator, and that is going on to the moon. It will land on the moon, hopefully again in a functional mode. And also we have a camera we developed, took an Azure Connect camera, commercial camera from Microsoft, and made it work for spacecraft. Yeah, using Linux Docker containers and stuff like that, the whole command language for it. This is the work of Don Haddad in my group. And finally, moving on to Sensei Media, smart materials, sensors getting into materials. It's an intriguing area for us. Ever since really the mid-2000s, I've been thinking of ways of taking sensor networks that are meters apart in the physical world, putting them within millimeters or centimeters of each other, so you have a computational fabric that senses and networks and computes as it flows, the way kind of the nervous system synapses and processes signals that come from our receptors. So we did lots of them over the years. I'll show quickly a few of them. We've got a paper that we published in IEEE Pervasive, really talking about the field in general and tracking some of the projects. Ermedy in my group is a PhD student coming from ETH, from Trosser's group, well-known group in wearables. Before he came, he had designed electronic dresses for Lady Gaga, it turns out. So we had some of that design talent in him, as well as being a really solid technical guy. He became kind of a weave master for Sensate materials. So he weaves structures that can measure stress, strain by how you weave it. You have piezoresistive elements you can integrate in. You can integrate other layers of fabric that can exhibit a response when you press or squeeze them or stretch them. It comes off of our knitting machine. My lab is now dominated by a large knitting machine. Ermedy is its master, and it's producing e-textiles. This is a keyboard he made that I can play. Capacitive keyboard. So it's like a scarf, it's flexible. But this is a keyboard that can change color. Well, anyway, I'll explain the keyboard. So if you put voltage on it, it can change color. And this is one, actually, you really do want to hear this. This is Ermidy's final keyboard. That works now. What keyboard can you stretch? You can measure it. This one you can't, because we measure stretch in the fabric. We measure pressure, we measure height. Is that still working? Okay. So he's measuring all these different things. Actually only getting one channel, I think. That's okay. Yeah, you're only getting one channel. That's my fault. Anyway, let me try one quick thing, because I got one or two more videos that have sound. Let's see if I can go back to this. Now that this is promising, actually. That worked. Okay, let's try. Try this again. I bet you it may work now. If it doesn't, well, it doesn't. So this is a keyboard player that's a bit better known than me by far. Jordan Rudess, how it works. He is the keyboardist for Dream Theater, a very well-known progressive rock band in the US, known worldwide. He's won multiple Grammys. And he saw the Fabric keyboard, won an award from the Media Association. So he got in touch with us to try to play it. He came over and did it. That's Jordan kind of pushing it a little bit here. He's going freeform in this video here, playing with the different kinds of sounds it can make. We have a grant for him to come to work with us this year on performance and AI. So to think of a virtuoso performer like Jordan, AI interpreting what he does, also other sensors beside the keyboard to see how his body is reacting, having the AI manifest through a set of dense set of lighting that he's going to be living inside of, and audio. So stay tuned for that. Come on. Come on. Ermdy also, let me go to slideshow, sorry. There. Also develops very dense sensate weaves using thermoform yarn, so it can actually take the shape of a sock or a slipper, but measure dense pressure. So if you want to look at gait dynamics, if people have trouble with their feet, you can now just put this on, wireless interface right from the thing, and as you're walking, just in the fabric itself, it builds you a pressure map. I got on the MIT homepage a while back, and you're seeing it here. As he's moving, you're seeing the pressure change. So this is like a sock, but it's a sensate sock, totally flexible. And he's built into carpets, doing interactive dance with them. This is a dancer on his carpet. So it's measuring where she is, how hard she's pressing. It's got an XY scan, 2 electrodes, X and Y, and it's got a piezo-sensitive element in the middle, piezo-resistive. And we're just mapping that into response. This is an event we did in Bangkok. It's traditional Thai dance performers on a carpet like this. This is machine learning. Again, it's going to happen with everything. Now he's using it to classify as different kind of walking and different kind of foot motion. So walk, run. He's also a yoga practitioner, so it can look at the different, all my emails coming in now, sorry. But he got distracted from his thesis project by a grant from Burning Man. And they saw the e-textile work he did. He won several design awards. They gave him money to do a huge e-textile installation, a massive kind of a teepee with sensate weaving in the fabric so people could interact with it that would be on display. So that was the design that he worked out. He actually wove a version on our knitting machine. These are the sensate electrodes. They're all in different kinds of patterns. Every one of these is a different kind of cultural identity. The patterns kind of reflect that. and they're all sensates. This is Ermity with them all stretched out in our atrium when he was trying to make them work. This is at Burning Man, so a whole MIT crew came to design the structure and put it up. It had to withstand 90-mile-an-hour winds. They designed it. That was a requirement. And in true MIT tradition, they did it. I'm glad they did. And of course, it's Burning Man. Who the hell knows what they do in there? But it ran for a day or two. But then, of course, the weather turned bad. So there were dust storms. They did have intense wind. They got pretty pummeled. And then it rained. So its life was cut short at Burning Man. But we brought it back to MIT. And this is Ermity running it. Can you crank this? Hopefully it works. You never know. It may not. But there's music that's coming from his motion. I think that's weird. This clip just does not want to work. I don't know why. You can hear a little bit there. You got to really crank it. That's a dancer that's working. It's measuring his position in between. It can see whether he's touching panels, which panel he touches as well. And as he's moving, it's doing things. Ermity has also done dense electronics and textiles for measuring biophysical parameters. This is what I'm having to do for his thesis, integrating, again, sensors and processing in flex electronics with a textile to measure many, many things. Build a sensor network into a textile. It's a dense one. And you can cut it, shape it. He's building that now. The results will come out by the summer. And then we've done versions of it on tape. This is the sensor tape. It's thinking about sensing as utility. So you have something like a tape. You can cut it where you want. It's the shape of a roll of tape. We have IMUs on it as well as other kinds of sensors. And again, you can bend it, recapture the shape just by plugging in at the end. It has also proximity sensors. You can make a little touch screen if you want, or capture geometry, or even capture posture. So here he's getting his back geometry. My student Cedric has made that on a tiny fiber. This is recent work, taking technology from the LED industry, stuff he developed actually in Shenzhen. So you have this tiny piece of flex circuitry, put inertial sensors and other sensors on it. You can make it quite long and really measure this parameter along the length of this almost a wire, almost a fiber. You can start to knit that into clothing. And then we flew a version on the space station. This is my student Juliana's project, putting piezoelectric fibers in a piece of beta cloth, a cloth that white-lined spacecraft to measure micrometeorite impacts. So we flew a passive and an active sample outside the space station a year or two ago, and that's it launching on a Falcon that was installed on the space station. That's it outside. These are her fibers. And indeed, we measured what looked to be hits. We may even have something that's almost like wind, right? There's atmosphere there. We can see a tidal effect as you go around the Earth. It's resonant with the orbit as you have atmospheric bulge. And there's some background from that. And then we do see discrete hits that come in too. So we could be measuring microparticle impacts. We have to do a little more analysis. We won the Aerospace Prize in the NASA Tech Briefs contest with it. And then we also won a grand prize that year. A project my student Ali did. It's a pneumatics toolkit. He calls it Flow.io, whole modular system to look at soft robotics and pneumatics. Just an amazing ecosystem. He's created it with people around the world using it and adding to it, adding new designs. Just incredible. He's built a whole following around this. And then we use it in spacesuits for astronauts, where we can compress the fluid in zero gravity flows to where it shouldn't be. We can actually compress the legs dynamically with this Flow.io, and then with Ermity's fabrics, measure how the body responds, measure the pressure that's there. Our magnetic boots I told you about. So this is the last part of the talk. I'll go quick. I'll just do 5 minutes, and then I think we'll open up for Q&A. I love concerts, you know that. This is at the Roundhouse in London. I had to give a keynote for the Dudley Department of Imperial College. I selected the night before Hawkwind were playing, one of my old favorite bands from way back. Some of you may remember them. This is what it became after quarantine. This is a French band. The French band is playing tomorrow, actually, the Ghost Rhythms. They played a concert at a festival in France. Of course, I watched it. I had my pet rabbit. I had speakers. I had a great display. It is not the same. It was great. I had good sound, good video, but it's not like being there. This was last night at Le Zebra in Belleville. Crank this. I was totally magnetized by this, totally taken by it. Yeah, and what is it, right? It's the performers, you can see them. It's the people near you being into it. There's an intensity and physical presence that we don't have virtually yet. I think it's a real frontier. How do we do it? How are we going to get there? I don't know. And again, seeing these French musicians that push such an intense edge in their music, I'm all there. It's just, this country has it. No one else does it quite like French. Maybe a little bit in Japan, but they learned it from the French. Just an incredible team. It's called Zool music. Anyway, yeah, back to remote presence, right? Quarantine happened. We're all on Zoom. This is my first group meeting during pandemic. No one was happy, right? We got used to it, but physical presence is still important. So my group has always been fascinated with this idea. We put sensors everywhere. How can we expand experience by connecting to them in different ways? How can we channel all this information into our perception in ways that really expand us? I wrote the cover article in Scientific American with one of my students about this a while back, inspired by some great science fiction by Vernor Vinge. I used to be a professor at San Diego State, really thinking about what this kind of a visceral experience could be. And yeah, we started doing it. This is the Doppel lab. This is the media lab. You can see sensors inside. This is what we call a digital twin now, right? Trying to bring this data into an animation. You can see these offices are too cold. This is the temperature humidity in the atrium. These are too cold if they're blue. They're hot if they're red. So through the animation, we kind of bring everything up to the user. Isn't bounded by the laws of physics. You can flow through, you can experience the building in different ways, people moving around. And then we had audio, and you want to turn this up. If people are talking and you're near a microphone in the virtual world, as well in the physical world, you can hear through, it tunnels through. But you cannot understand a word they say. So you crank it. He's laughing. You can't understand anything. And then we went outdoors. So the work at Tidmarsh Farms, one of our retired faculty co-owned a cranberry bog that she turned into a wetland. And we built an environmental sensor that could measure what goes on in the soil, see how the environment around, and be in a low power wireless network. Still running now there. Built over 100 of these. Put them in different kinds of environments on the property. This is a transect that we built. Of course, a wetland, stuff goes into the soil. It's expandable. Put all kinds of sensors that could go underground into the soil and connect back up to the sensor. Temperature over a year, so you can kind of see different years, see how it changes. This is response to rainfall up here, so you can see different hydration at different depths. This is diurnal temperature changing during the year and with depth. So we get all these profiles. Worked with wetland scientists to try to analyze that. But for us, let's bring this data into our virtual world with an animation like we did before. So this is a digital twin of the real marsh. The music comes from the sensor data as well. So when you sensor data updates, you see the bubble, you hear a little ping, the pitch and the timbre, the temperature and the humidity. So you're experiencing this landscape in a totally different way. And as you move around it, you experience the different locations. It's different views. We can change the view easily with the mapping. So again, it's bringing the physical world up to you in different ways. This is a different mapping, it's very localized. As you near the sensor node, you're hearing what physically happens there. But again, it's put together by a composer. It's an aesthetic experience as well as an informative one. And I think this is important. Artists are going to bring this world of interpreting all this other information up and close to people. So this is animals changing their appearance with the history of sensor data, working with audio. It's work actually that happened here in collaboration with people at Da Vinci and some of the other institutes, trying to identify birds way back actually before eBird and stuff like that, because we have microphones and we could do that. So different bird species, different other kind of birds during the day. Cicadas coming out at different times, different birds arriving at different times of year. All this, we have years of data. We can go back with AI and mine it, bring it back. I'm going to skip this quick. This is a project that I may have mentioned it before, but it's important because it's seeded collaboration with DaVinci. It's a project that Thomas is working on. We're going to talk about a WISP paper shortly after this. But we called it Here There. You have sensors all over, including microphones. You have someone in the real world that wants to connect with them. Can you start letting them hear through these things dynamically, like it's an extension of the ear? So it knows where you are. It knows how your head is facing. It knows where the sensors are. It can fade the right audio into the right ear. So it's as if you're there. And we don't do it by covering the ear. We use bone conduction. Important to leave the ears open. Thomas is looking actually with pass-through. You can do now with modern earbuds. You couldn't do it back then. But I think there's something special still about leaving the ear open. We'll see in this data. But yeah, we built this, 5-6 years ago. Tried it at Tidmarsh. And it's a totally different experience for people. It's like your ears are tremendously expanded. This is Dan Gager, who is a fellow at Bose, designed all of their noise-canceling earbuds and headphones. For him, it was a totally different experience. So he's, moving. He's hearing. He's never heard before. I go from hearing. This is the last thing I'm going to show. My student Patrick actually has got a collaboration with National Geographic. He's in Patagonia now. He left the same day I left for France. They seeded a collaboration with my group and different groups of National Geographic explorers to look at some needs that they have, design a sensor system to address them, and then go and deploy it. So he's in Patagonia looking at acoustically tracking these wild bees. They're the size of your thumb. They make some noise, but if you have a distributed acoustic system, you can start to track them accurately and identify individual bees and see where they're going. Also a collar for wild dogs to measure things. Stuff like this. He's built microphone arrays that you can put out in the wild. They're robust, high quality audio recording as well as directional audio capture. So that's in Svalbard. We deployed it. That's the bee he's tracking now in Patagonia. That's the device he's using. It physically tracks the bee with a distributed audio and it has a 360 camera. It will figure out where the bee is and point the camera to it, at least to direct the information from the camera. And we have also collaboration with Thai real estate company. Like what we did in Tidmarsh, to take all the sensor data. We're putting sensors in an urban forest there outside of Bangkok. And we're using AI to do the mapping. Instead of a set of rules that we did before that were hard-coded in, you just basically explain to the AI how you want the information from the sensors to change the music, give it examples of the kind of music you like. Here he trained on Balinese music. And then you have a totally different way to map data into sound. We're doing it also with a Large Hadron Collider now. We have a collaboration that we did years ago with the Atlas experiment. We're getting a real-time data feed. Before we had a set of rules that composers could use. We gave them a template. They could do pieces so you could hear collision data in real time through music. Now we're doing it through AI. So we're doing AI mapping, give it examples of what you want to hear, basically describe to it how you want the data to map onto it, and the music will come that way. We're going to show it, I think, at the LHCC conference. We're targeting it. It's going to be in Boston on Northeastern in June. So that's coming. Okay, I think I will stop here. Thank you very much. Sorry for the audio. There's definitely audio problems somewhere in this machine. I will find out one day what they are. Is there Q&A time? Or I guess we have a few minutes. It's getting noisy.
Questions?
Any questions?
There's a switch.
Any questions?
Yeah. We have one.
I don't know how this works. About the productivity glasses, you use them among the MIT right now, or all students use them for?
We use them at MIT for some of the studies in focus and flow that David Ramsey did. But now we're using them with international collaborators. So the Freeborg group use them both in Fribourg and buildings and also in Singapore, again, to look at distraction and focus versus comfort in these different environments. People are really intrigued by the environmental sensors. We see some indication of people feeling unwell with what we see in the volatile sensors, for example. This seems to be a correlation. It's early, but we have some indications that this could be true. There's a group in Sweden that came out of the workshop that wants us to make another 20 of them. So we hope to be able to make more. You know, they're not cheap, they're not terribly expensive either. They're in that middle place, but we only have 20 of them. We were going to make at one point 100 and use them in a Media Lab member event, but then quarantine hit. We'd stop having these big meetings. So we never made more than 20 to do our test with. But, you know, there seems to be a lot of interest. And we're going to add more sensors for the air quality. So we probably will do more. We're going to do more work, too, with smart HVAC. MIT, for some reason, knows me as the guy that looks at building systems and wearables and putting them together. Even though we did a lot of work before, there's no one in my group doing that now. We talk about a collaboration maybe with you guys as well on this. But the glasses are kind of part of that infrastructure because they're really measuring how people react and measuring the building as well with the air.
If you ever have one or two or let them think about this,
Okay.
I think all of us can be interested in being more focused in our work.
I agree completely, and these are relatively comfortable to wear. The question is, you can measure things that relate to it, but what's the intervention? So how clean is the measurement? It depends how structured, you know, the environment is to interpret it, but then what do you do? This is the critical thing. And yeah, ideally, you know, like in immediate atmospheres, you change the environment so that you can be more focused.
Hello, thank you very much for this amazing talk. I am also a researcher, but after what you have presented, I feel like so small. So, again, I have a question about the glasses.
Sure.
So I guess they give you the possibility to collect a tremendous amount of data.
Mm-hmm.
Have you started using any AI methods, deep learning methods to work with this data, to model it, to analyze it?
It's a good question. I don't think we have in the group. The Fribourg people may be starting to do it because they have most of the data, because they did the longitudinal studies in the buildings. I think that makes a lot more sense. You have to label it in the right way. I mean, there is some things you really have to do, but we have enough preliminary data so we can start to do that. So I think AI will be a big part of it going forward. So it's a great suggestion, and yeah.
Because
if we haven't done it already, we will.
If we combine, for example, all the data coming from the environmental sensors together with other data that we can collect from glasses like Meta glasses or Google glasses about more human factors, like attention factors, concentration, fatigue, etc. And we combine everything, the extrinsic and intrinsic factors of human activity, and we apply it in different environments, like in factories, for example. We can extract a very important knowledge about how humans react to different triggers and how human body, human states react to working process or learning process or rehabilitation process or whatever.
I mean, some of these glasses are an example of what part of the system is going to be. So we can build these systems now. They're going to get the data that's going to be relevant for this. I think moving forward, it's how the feedback also gets to the person, as I said before, right? Because we're going to live in an environment that's kind of a prosthetic extension of us. So this office is working to help us stay ideally focused and concentrated. Maybe if you look at what David Ramsey does, the way he has his life separated off, we can be put into environments like that, where it's not going to interrupt us. Already there's simple systems on these platforms that can do it, but they can be more responsive to our state because they know it. Are we in a position where we could be interrupted, where we could be a bit more distracted? Are we in a position where we really have to be focused? And these companion systems that would be probably AI driven are going to be a big part of mediating that. So this whole, how open is our bubble, I think will be a big part of it. And yeah, we're scratching at the beginning of that now.
So, do you hear me? Okay, so I'm a student in engineering school, so in data and AI. So I have a question. What should student interest in MIT Media Lab research should do next?
Sorry, could you repeat it a little louder, or what should students that are interested in MIT be studying, or?
Do you hear me? It's better?
Yeah.
What should do students interest in lab research should do?
What should they do? Just do great work. Do simplest thing, right? Do and follow your passions, right? Don't do something to get into the MIT Media Lab. Do something that you believe in, that you can put your all in, and try to break the mold. Try to do it in a way that's different from what other people would do. Okay, and the groups are all different. My group, we have wearable technology. We do a lot of sensing, a lot of representation. Other groups may do different things. But this is part of the rubric of reality now anyway, right? Lots of people start to do wearables. Break the mold. Do it in an interesting way and do it because you want to do it. And give it your all. That's really what the best advice I can give you. Sure.
Any other questions? Yeah.
I can't hear you. Maybe if you just kind of yell into it like
okay.
that. Okay, that's better.
About the sensor on the feet that produce music. Do you think this sensor can be used in the medical domain?
Oh yeah. You mean the thing I did in 1997, the sensors in the shoe that made the music? That I did it for music, but then I presented it at conferences. Doctors were there, and they approached me exactly about that. So I established a collaboration with the people that ran the Gate Lab at Mass General, the big hospital in Boston. And we made the first sensor network, sensor node for shoe that would do gait analysis with IMUs, with pressure sensors, bend sensors, many, many sensors. This was in 2001, 2002 that we did that work. So it was a natural thing. We did it, we published it, won awards for the paper, and then we went on to sports. So my group, you know, this is one thing, right? We change our work a lot. There's some groups that might work on the same thing. Like Ken Larson's group is a great example, right? They work on a platform for analyzing a city. They keep that platform, keep making it better. They give it to other people to use, and they, you know, keep working on it. We will do it for a year or two, maybe 3, 4 years, move on to something else. So yeah, we're not doing gait analysis so much anymore. And we did do all this work for smart HVAC, smart buildings. We left it to do these other things, but I think now we may come back to it with AI. It gets interesting again. We did kind of, well, let's get at the beginning. Get at the beginning of something. Show people what it can open up. Show people what it can do. And then I tend to move on to something else. But AI makes it different. We can go back now with these sensors, use that as the smart mapping to the building, whole different world. So yeah, we did that. It's a great example of the way the work follows on. But now so many things come back with different ways of looking at the data.
Thank you very much.
Sure.
Any other questions?
First of all, thank you so much for a very nice presentation.
Oh, my pleasure. You may want to talk closer. I think there's a squelch on it.
Okay.
Yeah, that's good.
Sorry. Yep. Thank you very much for a very nice presentation of a lot of great works. My question is more about the financing of your institution and the dynamic of ICE. Okay, sorry, thank you. So the dynamic of the projects that you have, is it more this dynamic because of the financing, or was there some projects that you really want to develop, but for example, the founders or some of the sponsors were not available, and you have to abandon some of these
that's
projects?
a really great question. At the Media Lab, we've been lucky for most of its time, where I've done all these projects because I wanted to do them, not because there was a sponsor that wanted to do it. Or if a sponsor was interested in something, I would take it and twist it so it's interesting, because what they wanted to do might be development. It didn't look too novel for us. We always try to look at something that's really a different way to approach it. So I've been lucky to be able to do that. The way we do it, at least traditionally, is that we have consortia. So companies, we used to have 100 companies in a consortia. So they're not funding necessarily an individual product, they're funding the lab. And you know, they will all find something interesting in the group of the 30 groups at the lab. They can plug into different groups at different levels. And then we do projects with them. They'll see what we do. Can you use it maybe in this context with Steelcase, right? We took their table, built our mediated atmospheres into a mobile platform that we wanted, but used their table. They took it back to Steelcase, used it in their research. There are many stories like that, where we'll take something that a member makes or sponsor makes, turn it into something different. They are interested and they'll take it back to the company and try to use it in their work. Or they'll come to us with an interesting problem. National Geographic coming to us with the Explorers. This is wonderful. We love exploration. And look, we got 100 ideas from Explorers. Most of them are awful, at least, or we couldn't do them because they didn't relate with what we wanted or were impossible. But we picked 3, 4, 5 that we can do. And this is great. We get a little funding. Now, National Geographic doesn't have a lot of money, but we get some, enough to be able to send our students out and do this work. So yeah, you want to keep the sponsor interested, keep the company interested. You don't want to do development for them because that's the kiss of death. Then you can't do anything that's breakthrough or innovative. So you have to get an exciting enough environment where they want to join, they want to contribute because it's really with the cutting edge, but they're not at the point to really tell you what to do. It's hard to do now, different environment. But the lab is keeping at it. We're still doing it. We still have the mojo, and we still have funding coming in to be able to do what we want to do. But yeah, you look at all the great places. Xerox PARC, another great example. Fantastic place. Bell Labs. They were doing kind of what they wanted to do in an environment that had the resources to do it. And I think that's so important if you want to get to this edge. If you really think about the practical application, it's there. But if you focus too much on that, it's going to kill you. But we have startups. Students are doing startups all the time. We even have an entrepreneurship program in the Media Lab. You build one here, I think, based on our E14 fund. At least I heard you were doing that. And that's one way of getting the work out as well, where you don't have to stop the research to perfect it. You can actually toss it to a startup and they can work. You want to find typically lead users, right? So a doctor that has an interesting problem, that there's no sensor that they can think of that can solve it. And we can think of a different way to do this measurement. So to find people that really are on top of some unsolvable problem that's really interesting. Those are the collaborators we love to have.
Do you have the time for one last question? Yes. So again, as a young researcher, I need your advice. Tell me, how do you deal with simultaneous supervision of a big number of PhD students? I mean, what you have presented is so big. And I guess that some of this work run simultaneously. How do you deal with this cognitive load?
This is a huge, I actually wrote, we all have to write expectations documents at one point. At MIT now we have a student union. You've had unions in France forever because that's how you work. My French students tell me, oh, union, of course, you should have them. We all have them. It was a shock for us. Unions, graduate students, how could you even think of it? We're getting used to it now, right? It's happened. We've thought a lot as MIT professors in general about how to manage the relationship advisor to student because it's so critical. It can get abusive because you have deadlines that you have to keep as an advisor. You don't want to put the pressure on the student to a point that it breaks them. How do you have the students motivated to really work for themselves? And that's what I do. I don't always tell them what to do. I find something that's really interesting for both of us. And that's going to be their life. They're going to walk out on the stage at Chi or WIST or at UberConf, one of the big conferences that we go to, and they're going to own the stage because they're going to talk about something that no one else is doing. So that's their motivation. They will work on this to do it. And then you pick them. You got to pick them right. You develop a sense of picking students after a while. And I tend to pick students that are very self-motivated, that don't have a strong ego, that really love to do good work, that have a track record of actually being able to do deep work. And they get along with others. They're more collaborative. For me, that's important. They're not competitive, they're collaborative. So that's how I built my group, and so far it's worked. Different groups have different models. And I write about the kingdom where there's the king, the federation where you have the postdocs, another way to do it, and the commune, which is kind of my group, one for all for one. So you have to find what works for you.
Thank you very much, Joe, for a fascinating talk. And thank you, everyone, for your attention and your reflective questions. So another round of applause for Joe Paradisio.
Thank you for your patience, too. Thank you very much.